Uh, okay, so I was just talking about the uh, purpose of the intake facility. The intake components, the intake systems essentially consists of several uh, unit operation. Uh, it might start from barrack, and water gets after passing the barrack, water will get into the intake structure and then processed through the intake conduit. And after that, water may pass the fire screens again before entering to the pumping stations before distributed to the treatment facilities. So these are the unit operation, which we normally consider as the part of the intake system. So the intake components are normally influenced by the several factors. For example, characteristics of water resource. If we use the surface water, so we need to concerns about the aquatic organisms. We need to concerns whether it would block the navigation systems or the transportation systems in the water or not, and many other factors we need to concern about the how we use that water resource. And we also need to concerns about the presence and the future capacities. As I told you, for the intake facilities, we need like a long-term use. So we need to decide for the next 40 to 50 years, unlike we do with the unit operations and unit processes in the water and wastewater treatment plant. In that case, we normally use only the short-term designs. That is why in the previous chapter, we were only talking about the population forecast for the next 10 years. We never predicted for longer than 20 years. So if you want to decide the unit operations and unit processes in water treatment or wastewater treatment plant. Water quality variations are, as I told you, sometimes the turbidity is high, but sometimes it's low. So intake facilities should actually accommodate such kind of wide variations in terms of both water qualities and water level. Climate conditions are in extremely cold climate where there is ice. So ice may cover the surface of the water resources. So sometimes we need to concerns about how we can withdraw the water. The port that we generally open to withdraw the water must be somewhere in the water. Not very near the surface, although the qualities of water near the surface would be better than the qualities of the water near the bottoms. But sometimes we need to withdraw the waters from the deeper port. The existing and the potential pollution sources, like in the case of Bangkok, we mostly use the water from Chao Phraya River. It's the major river in the central regions of Thailand. Many cities located along with this river, we all use the water from this river. So in the case of Bangkok, we actually build like a canal. We normally call it Klong Papa, and the point where we withdraw the water from the Chao Phraya River is located in Pathum Thani province in Sam Kok district, which is considered as the upstream to the Bangkok downtown. So it's actually several kilometers away, or the upstream with respect to the locations of the Bangkok downtown. But anyway, right now it may not be very upstream to the towns, because upstream to the points where we collect the water, there is Ayutthaya province, and then upstream to the Ayutthaya province, there is another province which also used and then discharged the waste into the Chao Phraya rivers. But anyway, concerning about the river, the city, the point where we locate the intake facility should be somewhere away from pollution sources. So for the Bangkok, the point where we collect the water is just uh, uh, few kilometers, actually few kilometers from Thammasat, from our campus. So if you go to the Pathum Thani province, you take the big road behind our university. So you cross the road and then get to the small communities on the other side of the road. So there will be a station, a water withdrawal station called สถานีสูบน้ำสำแล so you may have heard about this. And these stations, water is transported along with the canals to the treatment plant located in the downtown of Bangkok. It takes like around, I think, 40 kilometers to reach the water treatment plant. So the canals that we built is also part of the intake facility. That is why the intake facilities, the cost of the intake system might be accounted for 20% of the total water treatment plant investment. Other factors that we may have to consider, for example, the protections of the aquatic life. That is why we have to equip the intake structure with the screen before withdrawing the water into the intake facilities. Water variations, especially the river, in some river in the northern regions of our country, there is quite a wide variations in terms of water levels. During the dry seasons, the water level will be very low, but during the wet seasons, water level will be very high. So the intake port should actually accommodate such a wide heighted variations. Navigation hazards are foundation conditions. If you want to design the structures located in the water, we need to concern another types of force. You may have heard about the buoyancy force. It's a totally different from the force acting on the structure where you located on the ground. So in the water, you need to concern about the buoyancy force, in which the magnitude of this force is equivalent to the amount, the weight of water replaces by that structure. Sediment and bed load are sometimes the water they carry a lot of sediments, and sometimes it accumulated at the bottoms. So we have to be careful, because in the sediment there is a chance of toxic substance accumulation. So we should not withdraw the water from the locations or the positions near the sediments. So it should be somewhere above the some meters above the sediments, or the away from the bed loads. Require reliability. Uh, uh, no matter what is going to happen, but the intake facilities need to be able to supply the water. So there's an earthquake, or there's any other problems, there's floods, whatever the disaster that may occur, the intake facilities should actually be working. Otherwise, the community will not have any water supplying to the to to the people who live in the community. Economic considerations, of course, whatever we build it, we need to concerns about the budget. There are many types of the intakes, but we can actually classify it into two major types: the exposed types and the submerged types. The exposed types is a kind of intakes that we can see it from the ground, so it's above part of the intake structure located in the water, and some part it's above the water. For example, the towers intakes, which are located adjacent to the dams or besides the shore well, or sometimes we have the problems with the geographical conditions. We may have to use the floating intake, so the moving intakes, or sometimes we need to use the siphon well. So these are the exposed types of intakes. Sometimes we also use the submerged intake. So basically, we just put the pipe, install the pipe under the water. So exposed types and the submerged types has various considerations. For the exposed intake structure, this could be applicable for the larger systems. Submerged is only applicable for the smaller system. The larger system, we are not recommended to use these types of the intakes. Less expensive, and one of the advantages over the exposed types is it won't create any navigation effect, so it won't block the water transportations in the water. And also there's no impacts on the floating debris or the ice during the winter. But anyway, it's less flexibility because it's just a pipe installed under the water. So mostly it's fixed. We cannot adjust like the depth where we want to withdraw the water. Difficult in terms of the operations and maintenance. So whatever we put it under the water. So if you want to fix or if you want to replace some part of them for maintenance, so we have to driving into the water and then work under the water. So it's really difficult in terms of the operations and maintenance. But for the exposed intake, of course, it's really easy in terms of the operation and maintenance, but they may create the navigational impact. So these are the considerations, fundamental considerations to select what types of intakes to be used. So this is the reservoir intakes. The photograph is showing the reservoir intakes. Basically, these are intakes structures located next to the reservoir. So the constructions of this intake facilities must be done along with the constructions of the dams or the reservoir. So these types of intakes consist of various ports. Various pipe to withdraw the water at various depth. According to these figures, you would see three, pipes installed at various depths of the water. This one is located at the bottoms, and then the second one located some certain meters above the lower ports, and the third one is also the same, located above the the other two are pipes which we used to withdraw the water. So this will help us to select which port we can use. So if the qualities of water here in the bottoms is not good, then we only use the second or the third port to withdraw the water. But sometimes the water levels goes very low, uh, uh, and uh, sometimes it's even lower than the levels of the third port. So in that case, we may have to take the water from the other lower port, even though it's very near to the bottoms of the reservoir. So this is a kind of tower intake uh, we can use in case of if we use the reservoir water from the reservoir as the water resources for the community. Uh, these are the photograph showing the typical intake tower. According to this photo, there are two types of the intakes. The figure A is the wet intake, while the figure B is the dry intakes. The difference between these two intake facilities is this one, the water jacket, or according to this figure, they call the flooded chamber. So as I mentioned earlier, if we want to locate the intake structures into the water, we need to consider another force which may act on the structure. That force is typically noted as the uh, uh, buoyancy force. So buoyancy force acting on the structures in the upward direction, so opposite to the gravitational force. So in that case, if we want to locate this structure in the river, we need a heavy structures to balance with the buoyancy force. Uh, if we want to make it heavier, so we need a strong foundation, like in case of a figure B. So we need a thick wall of the uh, uh, intake chamber, and we need to put some foundations under the ground. So sometimes the construction cost is higher due to the effective foundations we need to use it. But for the wet intake, as the buoyancy force is concerned, so uh, if we go for the dry intake, we may have to use a very heavy structures. So if we have the problems with the uh, uh, geographical conditions, sometimes we cannot build a heavy or the strong foundations under the soil. We may use this method instead. So this wet intake essentially consists of the flood chamber outside. So there is another chamber. There are basically two chambers. Water entering to the intake facilities and then keep it inside the central part. Water is withdrawing from this chamber. This is the discharge pipe. Uh, this pipe bring the water inside these intake structures and send it to the water treatment plant. But the flood chamber, it's just once water gets inside, so the weight of waters will help to balance the buoyancy force. So basically, the purpose of having a flood chambers outside the intake a chamber is to balance the buoyancy force. So this type of structure as we already have the flat chamber, so water kept inside this chamber create lots of wedge. Then it helps to balance the buoyancy force. So in this case, we don't need to have a very strong foundations. So this is that is why the diagrams in a figure 8 we typically call the wet intake, because we use the water to balance the buoyancy force. But in the second pictures, there are no flat chamber. So in that case, we need to build a strong foundations. So these are the difference between a wet intakes and dry intakes. Uh, this is also the tower intake located in the lake. So the intake structures located in the water, and then there is the pumping facilities inside. So pumps with the waters from the lakes and then send it to the other uh, uh, treatment facilities, or in here uh, they use the compressor building uh, to keep the water before distributing, before sending the water into the water treatment plant. This one is also the reservoir intakes. So basically, it's just the tower located next to the dam, the earthen dam or the concrete dam. So these are the sketch. But anyway, in here, this is the uh, another types of the intake. So it's basically the square. It's essentially the square shapes. So here it's the other port located just few meters above the bottoms of the lakes, and there are ports around this square. Uh, Water can get into the tower in this direction, and then these directions, and another side, another directions in the opposite direction. So there are basically four directions that water can get into the intakes tower. So this is another types of the intakes facilities. We can use it in case of the lake. For the river with a high variations in terms of water levels, or very high fluctuations, some plants may use the floating intake structures, but mostly the plants that use the floating intakes, they may not be able to accommodate such a very large flow rates. So for the small treatment capacity, the floating intake may be suitable, but for the large scale production, it is better to use other types of the intakes facility. Floating intakes structure is just quite suitable for the small quantity of water required. Uh, this one is also the movable intakes. I think this one is one of the most common intake equipment that we could see in the rural area, especially the farmers. They use this one, these pumps to withdraw the water. And as this is the movable intake, so once they finish their job, they just dismantle and then bring it to their home. So this is how the people operate the movable intakes, and this is also good if there is water variation. So this one is a high and this one is low, uh, uh, so that these pumps can accommodate such a very high flow rate variations. Uh, this one is the photographs of the siphon well intakes. Basically, this is the intake chamber, and the pipe, it's equipped with the vacuum line to withdraw the water. The siphon, it's nothing but just try to create the negative pressures. And once the negative pressures is induced, so that the water can actually get into the pipes, and then finally keep the water in the chamber like this. This is called a siphon intakes. This one is a short intake structure, but sometimes the building they use these types of the structures. This is the photographs of the submerged intakes. As I told you, the submerged intakes is under the water. It's installed in the water. So no part of the submerged intakes emerge from the water. So the beneficial use of this one is it won't actually block the transportations in the water. But the major disadvantages that we have to consider is if they are, if we need, if they need the maintenance, we have to drive under the water to reach here, these positions, and fix it. So these are the photographs showing the various types of the submerged intakes. This one is also another types. This one is a screen pipe. The intake itself does not located in a water. It depends on the geographical conditions. So if the geographical conditions is something like this, so there is no need to keep the intakes inside water. Another types of the intake. So basically, it is the tower, but these types of intakes contains several port or several multiple inlet gates. Multiple inlet gates. There are up to 6 ports on this side. So if the water quality of if the qualities of water near the lower port is good, then we withdraw the water from the lower port. But if it's not that good, then we take the water from the middle port, or sometimes the upper port. So it's not always, it does not always to use just one or two ports. So you can use up to several ports like this, as long as we produce a good quality of water. So this is the multiple inlet gates. On this side, there are the gate along with the height of the tower. What we really concerns, one parameters that we really concerns about the raw water intakes is the aquatic organisms entering to the intake facilities. This actually could block the water movement. This is also the movable intakes. This one is equipped with the cable drum, so we can manage them. So sometimes if we want to hire a port, then we take this up. Okay. For the capacities, as I told you, for the designs and capacities, the intake facilities, we normally design it to handle, to withdraw the water over 40 years, sometimes 50 years, or it should be a long term, not just 10 or 20 years, especially for the tower intakes. Construction is not that easy in water. So once we build the dams, we need to build the intake tower along with the dam. That will be easier. Like in many projects, in many big mega projects in Bangkok, for example, the constructions of the MRT, the green lines, I think, passing the Pahonyotin road during passing uh, the market. What is the name of that market? I don't remember. One of the communities with a very dense populations uh, 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 along with the ถนนพหลโยธินนะฮะ ตลาดยิ่งเจริญokay, in that area, in fact, not just the not just the MRT construction. So once they opened the projects, once they start the project, so they not only uh, uh, built the MRT, but they also do the uh, piping uh, maintenance, replace the old water supply imply by the new one. So they have already done. They have already opened, take out the road surface. Then on the same times, it is better to do. It is better to change the communities, the infrastructures at the same time. So if they do it in the future, maybe that will be the problems. There will be a traffic. There will be many other problems arise. Constructions duplicate of the duplicate structures is common in the infrastructures designs, especially water and wastewater treatment facilities. We need to have at least 2 units. For the pumping facilities, the pumping system, you may have seen it somewhere. We never only use one pumps. We need at least 2 or 3 pumps in operation. So if there is one unit uh, uh, out of order, so that we still have 1 unit left. So that 1 unit which is left can be used for supplying the water. So if we only have 1 unit, so if this unit is broken or not functions for some reasons, then we will not be able to supply the water to the community. So normally the unit operations and unit processes in water and wastewater treatment, we need to have at least 2. According to the layout, photographs showing the layouts of the wastewater treatment plants I showed you in the first chapter, you will see that most of the unit operations or unit processes, they are having at least 2 units. The sedimentation tanks, there are 6 or 8 tanks, I'm not sure. Bioreactor, there are at least 2 reactors there. So it's important to make at least 2, even though we can make 1. But for the practical point of view, we better have 2 units. As I told you, because failures of the intake works means the failures of water supplying. And these are the location considerations. If we want to decide to locate the intake facilities, we need to consider the water quality. We need to consider the water depth, silt and sand. Locations should be, should have very less impacts from the silt and sands. Even though we have the systems to remove the silt particles and sands particles, but better to be avoided the location where there's a silt and sand accumulations, trash and debris, uh, the elevations, higher and lower elevations. So the locations where we locate the intakes should be somewhere in the upstream, and we should also consider the elevations. Another plants that we used to produce the water in the western side of the Bangkok area called the Mahasawat water treatment plants. I don't know whether you have heard this name or not. The Mahasawat water treatment plant, it's normally the plant we make a few visits almost every year, but unfortunately this semester we can't do that. Anyway, these plants produce the water and supplying to the people who live in Bangkok and suburban, especially on the western side of the Bangkok's or the another side of the Chao Phraya River. They actually take the water from the Meklong Dam, which is 100 something kilometers away from the plants, and the water is transported along with the canals like Klong Papa, and uh, the elevations of that of the intake facilities is higher. Uh, uh, I'm not sure, but few hundreds meters higher than the elevations of the Mahasawat water treatment plant, so that during water transportation, we don't need to provide it, the pumping facilities to lift up the uh, heat of the water. So if the elevations is already high, then we don't have to install any types of the pumping facilities to lift up the heat. That is why sometimes we need to consider the elevation. Treatment facilities cost least cost constants with the long-term performance, and operations and maintenance costs may be required. We need to consider this factor. River intake location should be outside the bank uh, and upstream to the source of the pollutions. We need to consider the variations in terms of the water quality and water quantity, or the water level. Flood considerations. We need to prevent the flotation as the buoyancy force is acting on our structure. So we should make it heavier, or at least balance the buoyancy force with other types of the wedge. Should consider for the flood stage in excess of those record, because the floods sometimes we cannot predict, but the intake facilities, river intake facilities should be able to handle whatever the flood stage. Silt and the bed load considerations. We have to consider the sediments traveling along with the river, and avoid withdrawing the water containing too much silt and sand into the system. Uh, if it gets into the system, so it will affect the moving equipment, especially pumps and some other mechanical equipment. It may cause abrasion, and for long-term abrasion, our pumps and other moving equipments may be damaged. So this we have to consider. For lake and reservoir, the location should be uh, 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 supply, should be able to supply uh, sufficient quantities of water with a consistent reliability. Uh, And we need to consider about the constructions, because constructions in the lakes and reservoir may not be very easy as compared to the river. And we need to think about the sedimentation problems, especially the reservoir. When we consider the reservoir, the reservoir, it's actually we used to build, we build the dam just to block the water and create a huge pond. Uh, it's just like this. Uh, okay, maybe I take a snipped. So this is the uh, Windows version. Somehow it's better than the Apple or Mac version. uh, okay, so this is the reservoir. This is the waterway. Then we block this waterway and create the reservoir. So usually it's something like this. This is the stream. So once the stream reach the reservoir, what will happen? As the cross-section areas of the reservoirs is quite large. So just think about the velocities. Velocities of liquids traveling along the river, so it might be higher. But here, just consider the cross sections of the water in front of the reservoir. So the cross sections in front of the reservoir it's very large as compared to the cross sectional areas of the rivers itself. So cross sectional areas, this one is much larger than the cross sectional areas of the river. So what will happen once the water reach the reservoir? The velocities here will drop significantly. So if the velocities drop significantly, there's a chance for the uh, suspended solids or the sediments accumulated here. So there will be a lot of suspended particles or the sediments accumulated in front of the reservoir. And if we and just imagine if we located the intake facilities right besides the dams or the reservoir. So what will happen? We need to handle. We need to withdraw the water with considering the amount of the sediments that may enter to our intake facilities. So this is we have to think about. But anyway, there in terms of the water height just in front of the dams or the reservoir, so usually it's 100 meters. So we have a lot of choice to withdraw the water to avoid the sediment problems. Uh, Anyway, the water quality impact on the intake locations depends on the pollutions and the potential at the intake site. Talking about the design intake capacities, for the intake capacities, if the design for it's given as a Q, so this is the presence capacity. So we need to think about the flow in the future, and we have to think about the minimum flows or the peak flows, which sometimes we call this as the ultimate flows. So the flows may be twice of the design's flow sometimes, but the minimum flows may be just 10 to 20% of the design's flow. And anyway, the intake facilities should be able to accommodate this very wide range of the flows from the minimums to the ultimate flows or the highest flow. Sometimes if the flows is greater than 1.25 or 1.5, uh, in this case, we normally consider as the hydraulic overload. Hydraulic overload, it's too much water, it's used. Sometimes we call the overload, but this one is just the amount of water used is higher than normal. That is why we call the hydraulic overload. So sometimes you may have heard about this term. Uh, Considering about the port selections, so for the plants with for the intakes facilities with multiple ports, multiple inlets gates, like in this photograph, uh, the selections of the ports of withdrawing water. If you want to concern about the organisms, you should actually take the intermediate ports or the deep ports. If you want to avoid the living organisms, we need to withdraw the water from the intermediates and the deep port. If we want to avoid warm water, we need to take the water from the intermediates and the deep ports. Storm turbidities. Anyway, it happened once in a while, so that it doesn't matter for the storm turbidity. Any locations, any ports could actually uh, withdraw it. Plankton, living organisms normally live near the surface in the shallow positions, but in the deeper positions, there will not be any species present, especially the producers like a plankton or uh, uh, plants which grows in the waters. Carbon dioxide. Carbon dioxide is rich in the water, uh, in the uh, 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 groundwater. So groundwater normally contains high carbon dioxide, especially for the lakes. You may find high carbon dioxide from water collected from the bottoms of the lakes. So if the depth is uh, large, then you may find carbon dioxide sometimes, which generated due to the biological activity. So if you want to avoid a carbon dioxide which creates the acidity and which may lead to the uh, 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 cause the corrosion in the piping system. So in that case, we need to take the water from the shallow water, shallow well, shallow port. So if you are taking the water from the shallow port, so you don't have to concerns about the carbon dioxide. Oxygen is there in the atmosphere. Then the oxygens can actually uh, get into the water, so that the amount of carbon dioxide is less. In this case, it is better to take the water from the shallow port. Iron and manganese, color, it is possible. If you want to avoid the iron and manganese, so you should take the water from the shallow or the intermediate port. So if you are going to take the water in the deep port, there is a high chance of finding irons and manganese in the water. Colors also, in the sediment, there might be a kind of uh, organic debris accumulations. So the organic extract could actually produce the true colors in the water. So in order to avoid the true color in water, we better take the water from the intermediate and the shallow port, not recommended to take the shower from the deeper port. So these are the port selections. Others are criteria, spacings of the ports. Vertical spacing should be 3 to 5 meters. The depths above the bottoms should be 1.5 to 2.4 meters. Depth below the surface variable depending on the qualities of water. Intermediate pore usually gives the best water qualities. So if you go back to this slides, you will find you are not recommended to withdraw the water from both shallow and the deep port, but intermediate port seems to be the best if we want to withdraw the water. Wave action. uh, Wave can actually attack the structures. So we should actually avoid creating the wave, or locations of our intake facilities should not be influenced by the wave actions. Normally, it might be like a 5 to 9 meters above the surface. So just in case if you want to avoid the wave action. Other considerations might be flotation, as the structure is located in water. So we have the concerns about the flotation, geotechnical, uh, mechanical, chemical equipment, fish protections. Sorry. So we need to prevent the fish to get into the chamber. Uh, Very funny stories if you visit the Bangkok uh, Metropolitan Waterworks authorities. The operators, they often found river shrimp bigger sized in the water treatment plant. I don't know how it gets into the sedimentation tank, but they often found big sized river shrimp. And do you know that's such a very big size? 1 kilo may cost like 1,200 baht or 1,200 baht. Very costly. The river shrimp, and they have found it in the water treatment plant. The fish also sometimes they have found in the sedimentation basin. So in order to avoid it, we should have like a kind of the screen to prevent the aquatic organisms entering to our plant, and sometimes it may get stuck in the pumping facilities. That is why we need to install the net or the screen to protect these uh, aquatic organisms, and also protect us from the possible contamination. Okay, now for the uh, intake facilities. Uh, The very first unit operation, which is part of the intake facilities, is the rack and the screen. The purpose of using a rack and a screen is to remove the suspended particulate matters from water. So we need to install a rack and screen. This probably is the very first unit operation we used in the water treatment system. This will help us to provide the protections to the downstream conduit, pumps, and other treatment facilities, and also can actually minimize the effects on fish. Uh, we can actually divide it into host screen, COARSE. I think A is missing coarse screen, or generally we call racks. So coarse screen means the opening pitch is quite large, like a 5 centimeters or even larger. So this is a kind of the coarse screen. Generally we call racks. And the fire screen also can be used to prevent the sand particles which may enter into the pumping facilities, because they are the moving equipment, and at the end they may cause the damage somehow. For the screen, as I mentioned, we can classify into a coarse screen and fine screen. And for the coarse screens and fine screens, we can actually classify it further. For coarse screens, we can divide it into two types: trash racks and the bar racks. The difference is just a clear opening areas. I mean, the difference between the bar racks and the trash racks. For the fire screen, the opening area is just a 6 to maximum 9 millimeters mesh cloth, and the basket screened. Usually, the opening areas is only 1.8 inches and to 3.8 inches. So this range is the most common for the basket screen. The last one is disc or a drummed screen. Uh, this one is also very easy. So the screen shapes is like a drums, and it's also always moving. Okay. Uh, there are two types of the drums, so it could be a vertical drums or the uh, other types of the drums. But anyway, the details of the rack and skin, there is only one issue relevant to the rack and screens is the head loss. Okay, uh, the for the small screen, fine screen, the head loss is higher. So we will talk about this again later in the next chapter. But in this chapter, I want to focus more on other components governed in the uh, 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 intake facilities. And these are the pictures showing the cost bar screen and the mechanical screen. This one is the this one is also the bar with the manually clean. This one is the bar with the automatically clean. There's facilities that we use to clean the screen automatically if the hair loss is going higher than the levels that we decide. So this equipment will remove the trash automatically. Anyway, we will discuss about this again later. So for the other uh, unit operation, which is part of the intake facilities, uh, sometimes we install the storage. Uh, we use the storage in combinations with the pumping facilities. Sometimes we use the storage in combinations with the pumping facilities before distributing the water to the household, or before withdrawing the water to the uh, uh, treatment facilities. So there are three major types of the distribution: gravity distribution, pumping without the storage, pumping with the storage. But the most commonly used methods is this one, the pumping with the storage. Unless you have very reliable water resources, you don't need storage. That is also possible. If you have like a lot of water resources, sometimes and the quality is good all the times, in that case we may not we may don't need we don't need this storage. But most community still uh, require the storage for some reasons, at least to accommodate the flow, okay, to regulate the flow. So here we begins with the storage. Then we talk about the pumping system later. The storage is the thing that we use. Uh, for example, we may use it like this. Uh, if you look back into the first chapter, you will find some flow diagram contains the storage. What is the beneficial use of the storage? So this is the inflow intake facilities. Then begins with the screen, followed by the probably the storage. And after the storage, we pump this water and bring this water into the treatment facilities, maybe the uh, rapid mixing or the coagulation, followed by the slow mixing or the fluctuations, and after that sedimentations. After sedimentation, it would be the filtrations. After filtrations it is the clear well. And then this is the unit operation where the chlorine is applied before distributing this water to the household. So the storage is equipped at the uh, uh, part of the primary treatment. So what is the functions of the storage in this case? Sometimes the water resources entering to the plants may not be very reliable. During the wet seasons, the flows is high. During the dry seasons, the flows is low. So it's never been constant. So the flows entering the plants is always like this. There is the fluctuation. But in the next unit operation, where we add the alum, as you have done the jar test last week, you will find the additions of the alums. The amount of alums used must be corresponding with the amount of the turbidity in the water. So if there is a Y variation, we will experience the difficulties in terms of maintaining the optimum alum dose. So in order to avoid that effects, what we can do, we can actually install the storage. The storage will do like this. The variation may comes from the nature, but before sending the water to the treatment process, we need to send the water with the constant flow rate. We need to send the water to the treatment process with the constant flow rate. So this is the constant flow rate. This one is the actual flow rates, which vary depending on many other factors. Sometimes there's a shortage, sometimes there is a flood like that. So never been constant here in the nature, but this process alums coagulation followed by the floculations, sedimentation, filter, clear well. So all these unit operation, we at least need very constant constant flow rates, constant uh, 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 quality. Okay, the quality. So we don't want the quality variations. We don't want to see the qualities variations. So in this case, what we can do, we can actually install the storage here. So storage will do like the inflow may be vary, but outflow need to be constant. So how to maintain the constant flow from the storage to the treatment facilities? We can simply install the pumps here inside this storage. So once we install the pumps, then we can send this water continuously with the constant flow rates. So what is the functions of the storage right now? So we used to equalize the pumping rate. Incoming pumping rate may be vary, but outgoing pumping rate need to be constant like this to equalize the supply and demand in the long term, and then to furnish the water during the emergency, like a fire during a fire demand. So we need to keep some certain amounts of water inside this chamber like that. So the storage provide the space to keep water during the emergency requirement. So this is the storage. And sometimes it may located here. This one is also considered as a storage. This is also the same thing, clear well. So just think about the clear well. So if we produce the constant flow rates, right? We apply the chlorine, but after the clear well, what will happen? After the clear well, we send water to the community's household, to each community's household. So in that case, the community household, they don't use the water for all the time. So sometimes they use, sometimes they don't use. Then the water use becoming like this. So just like what we had talked previously, there is a Q peak, there is a Q average. So there's variations again, but before entering to the clear well, the uh, flow rates is constant. So clear well is also act as the storage in this case. Okay, so this is the importance of having the storage inside as part of the water treatment uh, plant. And talking about the wastewater treatment plant, wastewater from the community get into the wastewater treatment plant, WWTP. This one is the WTP, water treatment plant. This one is the wastewater treatment plant. Okay, raw wastewater uh, get into the wastewater treatment plant. Before getting into the wastewater treatment plant, we also need the storage. Why we really need the storage? Because the wastewater generated from the household, there may be vary. They will never be constant. But after passing the storage, there be a uh, pumps the water into the water treatment plant. So in water treatment plants, the unit operation essentially used to treat the water. We provide the chamber with the oxygens, and after this, uh, we need to have the sedimentation tanks and so on. This one, this wastewater treatment plant, especially the plants treating the organic substance measured in terms of the BOD. So it is uh, according to the process we call the biological process. So the BOD or the organic substance get degraded. Okay, the degradation requires the oxygens and then some amounts of the microorganisms, and then convert this into the harmless end products. So this one, it's a biological process. It needs constant flow rates. But this one, before entering to the plants, there is a wide variation. Okay, so for the living organisms, for the the biological process, uh, this process is driven by the microorganisms, by the living organisms. So if they live in a favor condition, these reactions will proceed very fast. But if the microorganisms does not live in a good or the healthy conditions, we will experience the problem. So in order to keep the uh, preferable conditions to the bacteria or the living organisms, we need to supply the water, wastewater into the plants uh, with the constant flow rate. But entering to the storage, there may be flows variation. So it's just like a case of the water treatment plant. Uh, where are we now? Okay, there are too many pages on my screen. Just a moment. So after keep talking for almost 2 hours, so I need some hot tea. This is actually the tea from Taiwan. I've been there last year, maybe last December 2019. Actually, at that time, I went to Japan, but taking the planes, it was actually stopped over at the Taipei, and at that time I bought the oolong tea. This one is actually good. In the cities, they actually sells the price is actually per 600 grams, or in Chinese they call jang, maybe. They don't sell like a per 100 grams per kilograms. In Yaowarat, maybe they sell like the tea per kilograms, but in Taiwan, they sell per jang. But this one is actually good. Uh, Taiwan is a halfway actually to Japan. From Thailand, it takes approximately 6 hours from Bangkok to the major cities in Japan. And one time, I was traveling to Europe. Uh, uh, I'm not sure, Croatia or something. Croatia, it must be Croatia. And then uh, that city, it's a small city, it's very beautiful city on the Aegean Seas, a coastal town or in the Aegean Seas. Aegean or it's on the Balkan Peninsula. But anyway, they think like the Asian people are all the same. They cannot, differentiate who are Chinese, who are Taiwanese, who are Japanese, who are Thai. The European people, Actually, they cannot differentiate. And then maybe one ladies, they are really interested in Chinese or something. They asked me, do you understand the Chinese? Can you read it? And I said, of course I cannot. This is totally different from our mother language. And they just wondered why. Maybe they just compare with the Europe, with the many countries in Europe. At least they understand something with each other, although the language are completely different, but there are some certain vocabs, some certain words are quite similar. But in the Asia, it's totally different. And I told them, man, from Croatia to Italy, it may take like 1 hour by flights. From Italy to from Rome to Paris, it may take like 1.5 hours maximum. But look, from Bangkok to Tokyo, it takes 6 hours. So just imagine from Rome to where it takes 6 hours. It's out of the Europe continent. So in Asia, it quite actually variety in terms of the language and uh, how the people live. Okay, so that is uh, some small thing we learned when we travel. Okay, just come back to our topic, the storage again. Uh, Here are the details about the storage. So the storage, you may think like something like this, or you may think like the earthen ponds, just like the pond in front of our faculty building. Uh, it can be a storage anyway. So what is the purpose of the storage? Yes, of course, we used to equalize the supplies and demand, but anyway, we need the storage. So sometimes the storage is used as the elevated tanks to maintain the pressures or the heat. This is the pumping station, and this is the elevated tank. So we supply the water from the elevated tanks to the community. So as per the community's demand, during the high demand, the hydraulic grade lights may be dropped. So as the pumps we use to bring the waters to the elevated tank, so that the energies level should be higher than the energies with respect to the elevated tanks. So this is the profile of the hydraulic grade line. A pumping station should be higher than the elevated tanks. But anyway, during the high consumptions, this hydraulic grade line may drop due to the consumptions in the community. So the capacities of the elevated tanks or the size of the elevated tanks, the storage tanks. Here is the storage tanks, but they're not only used for the equalizing the supplies and demand, but they also used for maintaining the hydraulic grade line like this. So for this, the size can be determined. But anyway, how big is this elevated tanks that depends on the flow variations, the incoming flow variations, and then the demand. So incoming flows come from the pumps, pumping stations, but outgoing flows uh, or the supply to the communities depends on the demand. So in here, we can say that the flows entering to the elevated tanks can be actually constant, as this one becomes directly from the water treatment plant. But here, uh, So this one bring this water into the elevated tanks, and then the elevated tanks supply the water to the community. So uh, the outgoing flows may be vary depending on the uh, demand. And again, how we can determine the size of the storage. That is what we are going to discuss before uh, uh, the afternoon, before having a lunch. So for the size of the storage, all the sometimes we call the reservoir capacities. So the size of the storage can be determined by considering the inflows and the outflow. By the concepts, the size of the storage tanks it's equivalent to the difference between inflows and the outflow. If you take the inflow subtracted by the outflows, you get the difference. And this difference is the change in the storage volumes. So we need to provide these volumes for the water. But according to these concepts, uh, it's really difficult to imagine how we can obtain it, the the size. But anyway, according to these concepts, we can actually establish the method to determine the size of the storage. Uh, we can actually apply at least two methods to determine the storage capacities. Uh, the first method is called the graphical method. So by the name, we all know that we need to plot the curve. And then the second method is the analytical method. So this method, you just only put the informations into the table, and then probably use the Microsoft Excel to solve for the size of the storage. Okay, so we are now going to determine the storage size. So just have a look in the first example. So in this example, uh, it is about the reservoir. So we are going to determine the reservoir's capacity. So in this question, uh, consider an impounding reservoir that is expected to provide a constant draft. Draft is the amount of water withdrawal, 637 million gallon, or equivalent to okay, million gallon per square mile per year. So this is the amounts of water that the community need per year. Okay, 637 million gallon per year. And according to the record, it was showing like this. So just have a look the information in this table. The information is like this. In January, the inflows which gets into the reservoir is just 37.2. I'm not sure what is the unit. Okay, so this is our reservoir, very large reservoir. Our inflow in each month are valley. Sometimes it's high, but sometimes it's low. So you can see like there's a variation in January, February, March, and so on. But this community need a constant volumes of water to uh, produce the taps water. So they basically need the constant amounts of water uh, for a consumption purposes. what kind of consumption I don't know, but they at least required uh, uh, this amount, 637 million gallon per year, uh, to to be used in various purposes. Anyway, these 637 million gallon per year are is actually uh, can be drawn from the reservoir. So the inflow, our inflow is just like this. January 37.2. In February, the flow is almost double, 64.8. In March, very large inflow, 108. In some months, probably July, it's just 2.4 only, not that much higher. And then August, September, October, November, December, and then next year, January, it becomes a 60 again. So according to this example, then if we want to withdraw the water with a constant volumes, approximately 53.1 in each month. In each month, we need at least 53.1. So the draft is the water withdrawal. We need only this constant flow rates in each month. So according to this, how we can determine the size of the this reservoir. So what should be the volumes of this reservoir? So just imagine about the reservoir. Water levels, it's always vary, constant flow rate. During March, water levels may be higher, but in some months like April, inflow is just only 12. Water levels may be decreased. But anyway, even it decreased, it should be able to uh, supply the constant demand from the community. So in this case, how we can determine the volumes of this reservoir? The volumes of this reservoir should be large enough to handle the maximum inflows and minimum inflows. So there will be a fluctuation in terms of water levels or water volumes during the operation, because the inflow, it's not constant. Sometimes some months is high, some months is low. During the lowest month, the water levels may reach the lowest. But during the peak months, the water levels will reach the maximum. So we are talking about the size or the volumes of water here, variation. So what should be the water? What should be the volumes of the water variations in here? So the volumes required. So how can we determine? There are some certain procedures that you can find out. If you use the analytical method, it is recommended to do like this. You can take like a deficiency, a draft subtracted by the inflows, outflows subtracted by the inflow, it becomes a deficiency. So this one, the draft is higher than the inflow. So inflow is not enough. Okay, so deficiency is the 15.9. So you take 53.1 minus 37.2, you get 53.9. But in the second month or a month of January, inflow is greater than the draft. So we have extra amounts of water. Okay, because the draft is just 53.1, but the inflow is 64.8. So if you are taking the draft minus by the inflow, so you get some amount of water left. Sorry, similar to the March, the inflow is 108, but the outflow is just 53.1. So the deficiency is not what we don't face the water shortage problems in this month, but we have extra quantities of water left. Okay, so we should actually keep the space for them. And then next month we do the same. We'll do the same. So finally we get something like this. This information is for the entire year. Some months is getting minus, some months is getting a positive value. So next, what we will do, we will determine, we will only focus on the deficiency. The months that we find that we will experience the water shortage, like January, we need extra 15.9. And a month of April, we need extra at least 41.1. And similar to May, June, July, August, and September, we still need some water because it's the deficiency. It's giving a positive sign. So in here, we will consider only the months which the water shortage. So for the first month, 15.9, but after that, the second month we already have some extra amounts of water. Then we don't consider this month. And again, in this month, in March, we still have extra amounts of water. Then we don't consider this month. But from April to September, so we are going to experience the water shortage. So we have to take the cumulative deficiency for the April, then combined with the amounts of shortage in May, then combined it with the amounts of shortage in June, July, August, and finally September. So this one is the maximum shortage. Maximum shortage based on the 4 or 5 months. But in October, then we experienced no shortage, and on the other hand, we get some amounts of water spare, similar to November, but again December we find the water shortage. So we only consider the deficiency in this case. Only positive values of the cumulative deficiencies are tabulated. This is the explanations to the last far left, far right columns. And in this table, we can actually say that the maximum cumulative deficiency, according to this column, so there are 3 cumulative deficiency we obtained. 15.9, that is one. 202.2, that is the second cumulative deficiency. And then the last one is the 26.7 cumulative deficiency, though there is just only 1 month in this case, similar to the January, it's just only 1 month. So we have 3 cumulative deficiency, but we only consider the maximum cumulative deficiency. This one is not maximum. This one is also not maximum. The maximum one is 202. So this 202 will be the capacities of the storage. So we need to provide the storage with the capacity at least 202. So this will be the storage capacity. Okay, the storage capacities is the cumulative deficiency according to this table. So this is the method of the analysis or analytical method. we basically use the information. We basically use the tablet forms to determine the storage capacity. So the storage capacity is equivalent to the maximum cumulative deficiency. In this example, it is 202. So 202 is the answer. So to the questions to the storage volumes. So if you are about to find what should be the storage capacity, so it should be 202. Okay, so this is a method of computation. We use this method to determine the size of the storage. The method that I've just talked about is the analytical method. Okay, so maximum cumulative deficiency is 202, which occur in September. So the number of months of the draft is so this is the volumes. This one is the volumes, and this one is the average withdrawal rate. So if you take the volumes divided by the flow rate, if you take the volumes divided by the flow rates, this is the volumes of the storage. This one is the volumes of the storage. What is the unit of volumes? Cubic meters, right? And then this one is the flow rate, Q. What is the unit of flows? Supposed to be cubic meters per day. So if you take V divided by Q, what will happen? If you take like a V divided by Q, what will happen? What you will get, the volume V, the unit is cubic meter. What the flow rate Q, the unit is cubic meters per day. So finally, you will get per this one is per day, right? So finally, you will get the units in terms of day. Uh, so that V divided by Q, we can say that this is the detention time or retention time. Sometimes we call a retention time. Sometimes we call a detention time. Sometimes we call it hydraulic retention time. Or in short, we call it HRT. Okay, so the times that this storage can store the water, it's 3.8 months. 3.8 months. Okay, so this is the first example using the methods of computations, analytical methods to determine the size of the reservoir. About the graphical method. So I just want to show you like this. Okay, so this is the so I'm now on the Microsoft Excel screen. So if you don't see this one, just tell me. Hopefully you are now with me on the my Excel screens, Microsoft Excel screens. So just have a look here. This is the demand in over 24 hours, starting from the midnight and 1 a.m. in the early morning, 2 a.m., 3 a.m., 0 hours, the first hours. So for the first hours, the demand is this much cubic meters per minute. The unit is given as the cubic meters per minute. But in order to calculate it, to determine the volumes, it is recommended to convert the units to be in hours. Since we are going to analyze the flow rates in each hours over 24 hours, so the flow rates should be converted into cubic meters per hours. So the units are corresponding with each other. It's easy to get the results at the end. So if you convert the units, this is the cubic meters per hour, and this one is hours. But if you use like a cubic meters per minute, sometimes it doesn't give a reasonable value, or sometimes you make a mistake at the end. So it's recommended to convert it, this into the same unit. So this one is the demand. This one is the demand. This is opposite. Okay, the demand vary. Sorry. Uh, okay, this one is the water entering to the plants. So it will be something like uh, similar to this one, but here we are talking about the flow over 12 months. But in the examples I'm going to show you, it is the flows over 24 hours. So we are going to determine the volumes, and then uh, the demands or the inflows. Actually, not the it's a demands, but it refers to the amounts of water entering to the uh, to the storage, but supplying its constant. Okay, the words that they use here may not be. Uh, we better change to the inflow. Actually, it is the demand from the community. Uh, the demand from the community, but we are going to produce the constant flow rates. Okay, we are going to produce the constant flow rates, but the demand is actually vary. So in here, if you want to determine the volumes of the storage, you should do like this. This is the demands in terms of cubic meters per hour. Then, uh, if we produced with the average flows, so that we are taking the average flow over 24 hours, we are going to determine the average flow rates. What we can do it by just take 24 summations of 24 hours and divided by 24, the average value of this. So you will get the average flows over 24 hours. Then we pumped constant flow rates. So with this one, with the constant flow rates, the difference in demands and the average flows, we take the difference. So this one is the uh, average flow. This one is the demand. So if you take like a demand subtracted by the average flows, you will get positive and negative. The one which give a positive, uh, this one I'm taking average minus the demand. So if you are taking this one like this, you will get the positive value. But here, if you are taking this one minus this one, you will get the negative value. Basically, we will get both negative and positive value. But anyway, summations of the negative and positive value should be the same. And this one will also be equal to the amounts of the water that we need to provide the space water required, or this one is the storage capacity. So positive and negative value should be the same. Summations of the positive value should give the same value. Summation of the positive values in these columns, summations of the negative values in this column should be the same. Okay, so this is how we determine by using uh, uh, analytical method. Another way to determine the storage volume by using the analytical method. On the other hand, if you want to use the graphical method, so how can we do? I would just pick a file from the Microsoft team which is already there in your computer. So you can actually go to the files, and within the folders other reading materials, you will see like a 24 hours pumping. It's photographs. So I have taken from the textbook. This one is just similar to the previous sample. So we have the variations of flows over 24 hours. And then we need only 24 hours pumping rate. This is the constant pumping rates, which is equal to the average flows. So if you're going to take the flows in each individual hours divided summations of the flows from each individual hours, then divided by 24, it becomes the average flow. So the average flow, it's this amount constant, and this one is the peak flows. We'll know that. Okay. So this is the average flows or the average pumping rates. This is the requirement. This is the requirement. Okay. But this one is the birth, the pumping rate. This one is the birth, the pumping rate. This one is the rates that we use to pump the water and put it into the storage. But this one is the water requirement. Okay. So the amounts of water required, which is greater than the amounts of pumping rate, we need to provide the storage. So just like a curve, we have two curves in the mathematics. We have two curves in mathematics. We are interested in these two functions. So if you want to determine the volumes of the storage required, what you can do here, the x-axis is hours, 24 hours, times of the day, and y-axis is the flow rate, given as the volumes per time. Volumes per time. So this one is the time. This one is the volumes per time. All the flow rates. Considering these two functions, this is the water use, and this one is the pumping rate. The areas in between is equivalent to the storage volumes required. So the shaded areas in between these two lines is the equivalent to the storage volumes. We are going to determine the storage volumes. So how we can determine? So it's equal to the shaded areas in between these two lines. Why the shaded areas becomes the storage volumes? How can the shaded areas become the storage volumes? So this is the pumping rate. This is the demand. This line represents the pumping rate. This line represents the demand. The demand, which is higher than the pumping rate, we need to store the water. Okay, but how come the shaded areas is equivalent to the storage volume? What is the volume is expressed in terms of cubic meters probably. How come the shaded areas are equivalent to the storage volumes? If you look into the axis, x-axis given as the times, y-axis is given as the flow rates, which is volume divided by time. If you take x into y, so it becomes like you're taking the flow rates into the time. What is the unit of the flow? Volumes divided by time, and then this is the time. So this amount and this amount get cancelled, then you only get the volumes. What is left is just the volume. That is why if you could actually determine the shaded area based on this graph, so this will be equal to the storage volume required. But in order to get the shaded area, which would be very difficult in terms of the mathematical points of view, you may have to integrate, right? In the calculus, you have done this kind of function once. I'm not sure in the first or second mathematical course. I'm not sure, but it's there. So you have to determine the shaded area by using the integration. But if you don't integrate, what you have to do, you may use the Simpson rules to determine the area in each strip, which is very difficult. But we have another way to determine this shaded area. We are not going to plot it like this. Instead of plotting the graphs like this to determine the storage volumes, we don't do this way. We don't plot the information with respect to the times, but we rather plot the cumulative flow with respect to time instead. So if we plot the cumulative flow with respect to times, what we are supposed to get at 0 hours, so it's going to be 0, and then the first hour, second hours. So how the curve will look like? The curve will look like something like this, as it is the cumulative flow. That is why the line should actually goes up, not goes down. Okay, so it should be something like this. This is the time, and then this is the cumulative flow. So it should be something like this. If we are going to plot the cumulative flow, so how it will look like? So I just closed these figures, and then just come to the another figures in the files. Just a moment. Sometimes the computer gets slower, but not because of the heat. This room in my office is good, but doesn't have a preview. What's wrong with this file? Okay, now it's coming. Okay, so if you plot the cumulative demand and the cumulative pumping rate, you will see something like this. You will get two curves together. There are two lines. One line is the average flow. Another line is the cumulative demand. That is why if you plot the cumulative demand and the cumulative pumping rate, you will get the two lines. For the cumulative demand, you will get the curve like this. It's more or less like a S curve, more or less like a S curve. And for the cumulative pumping rate, as the pumping rate it's quite it's constant from time to time. So cumulative pumping rate, if you plot the cumulative, you're supposed to get like a straight line like this. This is the cumulative pumping rates over 24 hours. Okay. So for this, you can determine the volumes of the storage. The volumes of the storage can be simply determined by, just listen carefully, the volumes of the storage can be determined by establish the tangent parallel to the cumulative pumping rate. Establish the tangents parallel to the cumulative pumping rate. So what are the tangents we are going to establish? This one, the lines AB. And the tangent that we establish should actually touch anywhere on the these two lines. Okay, so this is the tangent that we are going to establish. Maximum vertical tangent is equivalent to the required storage. Maximum vertical tangent that we are established is equivalent to the required storage. So if you establish the tangent AB, that is 1, you may establish another tangent here, but this will still not give a maximum vertical distance. Maximum vertical distance, you will get only the tangent that you are established must touch the point C like this. So the tangent must be, parallel to the cumulative pumping rate. So these two lines must be parallel with each other. And this one again, the tangent must be parallel to the cumulative pumping rate. And the vertical pumping rate, the vertical distance for a maximum vertical distance between the two tangents. Maximum vertical distance between two tangents is equivalent to the required storage. So according to this figure, this gives the maximum value. Then this will be equivalent to the required the storage. Okay. So in some cases, it may be something like this. This is another page. This is actually the figures. I hope you are now on my figure showing the reservoir capacity. This is the picture showing the reservoir capacities determination. There is an inflow over several years, starting from several months in 1943 and so on. That's why you are getting the curve like this. So this is the demand, or this is the inflow. But the demand is this one. This is the demand, just like at the average lies. So it's like the lines, straight line in the previous figures, but they don't put it together. Otherwise, it will mix up, difficult to look into. Anyway, this is the average flow. Okay. So according to the procedure that I have just recommended, vertical distance, maximum vertical distance of the tangent is equivalent to the storage volume. Here in this graph, there may be many, vertical tangents. This one is also the vertical tangents, but if you are going to determine this one again, this is also the vertical tangents. And then if you're going to determine like this one is also the tangents parallel to this one. So maximum vertical maximum vertical distance will be equivalent to the storage volumes. This one, you can find the vertical tangents. This one, you can also find the vertical tangents, but they are not the maximum. The maximum is this one. So which one is giving a maximum value? We will take it. We will take that one. So just come back to the example in the Excel files again. So I'm now in the Excel screen. So if you don't see the Excel files, so just tell me again. Okay, I'll just make it smaller. It's difficult to see the number, but you will see the overall graphs. Okay, so this one is the plots of the cumulative demand against hours. So it gives like a S curve. Okay, and then we plot the cumulative average. You get this a straight line like this. This is the straight line for the average flow. So if you want to determine the volumes by using the graphical method like this, maybe you can try it. Repeat trying again. Okay, so I will just establish the tangent line, which is parallel to the average pumping. And then this line should actually touch the water demand somewhere. So suppose it is something like this. Then what is the storage volumes? The storage volumes should be, equivalent to the storage volumes should be equivalent to maximum vertical distance between these two tangents. And even though you are going to find the value from this graph, but it should give the same volumes that you obtained from the analytical methods. Here you should get like a 97.875. It's the same you get from this results, or you can use the analytical methods that I suggest. Both methods are basically the same, but just different way of achieving the number. Okay, so this is how we determine the pumping, the storage capacities. So if there is a pumping facilities not corresponding with the inflows or outflows. So sometimes it may be like this. This is the storage. This is the storage. So the inflow may vary, but the outflow may be constant. Sometimes the outflow is constant, but inflow may vary. So it is possible to get this either the first or second situation. Sometimes we need to design the storage to accommodate the the uh, variety of the demand. Sometimes we need to design the storage capacity with respect to the constant flow rates like this. So for example, this one is a clear well. Because in the clear well, this one is the more or less like the storage. We keep the water inside before distributing to the community. So for the community, they used a variety of water. But this one is the storage before coagulations and flocculations. Normally, the incoming flows vary, but the outgoing flows are constant. So if it's not constant, it will affect the performance of the uh, what I'm going to say is it will affect the performance of the coagulations and flocculations later. So if the flow is not constant, okay. So these are the methods, two methods that we use to determine the storage capacities. A little bit more complicated. So this one is like the water treatment plant operated 24 hours continuously. But if the treatment plant does not operate it for 24 hours continuously, maybe they use the chemical process. That is why uh, it doesn't have to be 24 hours continuously because the chemical process can be applied and then maybe they'll do it later. So for this, it's only 12 hours pumping. 12 hours pumping, not 24 hours pumping. So the pumping will pumping system will start. The pumps will start pumping from 6 o'clock. From 6 o'clock, not 0 o'clock. From 6 o'clock, they start pumping. And as they will operate it for 12 hours only. So these plants will operate for 12 hours only. So start pumping from 6 hours. What time it will be end? After 12 hours. So it will end it at 6 hours in the evening. Okay. So 6 hours in the evening. In this case, again, if you would have to determine the vertical distance, if you would have to determine the vertical distance, what you would need to do, the same concept we need to apply it. Establish the tangent parallel to the cumulative pumping. So which one is the cumulative pumping? This one is the cumulative pumping line. This one. But the cumulative pumping, we start pumps, operate the pumps at 6 o'clock, not 24 hours. So we start pumping at 6 o'clock. That is why the cumulative pumping rates begins from here at point E. And we take the summations of flows over 24 hours, but divided by 12. Previously, we take the summation of flows divided by 24. This is the average flows. But this one, the average flow, it's 12 only. So then at each hours, the amounts of flows will be different. The lines becomes like this. This is the lines for the cumulative pumping over 12 hours, but the demand is for 24 hours. Then this is the same line, the demand, 24 hours, but just the problems, our problems is we only operate the system for 12 hours, from 6 hours in the 6 o'clock in the morning until the 6 o'clock in the evening. So what we can determine, again, we apply the same concepts, but be careful. The tangents, maximum tangents will only be obtained by establish and touch that tangents at the point starting from 6 o'clock. Only with this point you will get a maximum tangents at the end. Here it's the point A. Then we establish the line which parallel to the cumulative pumping. So once you establish these lines and then move it up to touch the line set point A. So this is the line. So if you combine the lines, if you compare this line with this line, you will definitely get here as the maximum vertical distance from point C to point B. This one you will definitely get the maximum vertical distance. Okay, so this is the maximum vertical distance. No other points you will get the maximum vertical distance in this case. Okay, there is only this way. This is the only way to obtain the maximum vertical distance according to 12 hours pumping rate. Okay, so how we can determine in this case for the analytical method. So for analytical methods, it's a simple, or just a moment, my Excel files is not responding เป็นอะไรเนี่ย okay. Here the same informations starting from 0 hours and then the demand. So just look at my Excel files. So this is the previous table I show you, the one which highlighted with the yellow. So the columns, the information showing in the third columns of the second table, and the here the third column in the first table are basically the same. Okay, so these two are the same information, but the difference is just here. Are summations of the flows after converted into cubic meters per hours. You are strongly recommended to convert it into per hours, because here we are talking about per hours. The demand should also be presented in terms of cubic meters per hours to avoid any further mistake. So once you get this one, then you get the average pumping rate. Be careful, the average pumping rate is per 12 hours, because we are going to operate the pumps for only 12 hours, not 24 hours. Okay, so if you divide it by 12, the average flow would be 37.67. But here, if you divide it by 24, you would get 18.8. Okay, now for the average pumping, so as the pumps is operated for 12 hours only, starting from 6 a.m. in the morning. So for the average flow at the end of 7 o'clock, here is the average flow. Okay, so the same procedure, you may take like a comparisons between an outflows and inflow. Some you will get the negative value, and some you will get the positive value. Okay, this column, sorry. Some are negative and some are positive. So this column it's a positive, this one is a negative. But anyway, at the end, positive or negative would definitely yield the same result, which is equal to 171 cubic meters. So the storage capacities in these questions should be at least 171 cubic meters. Okay. So it's of course larger than 24 hours pumping, because 24 hours pumping the system is in operation for all the times, but this one we only work for 12 hours. So the size of the storage should be larger. Okay. So this is about the storage uh, capacity determination. Okay, now we are uh, uh, approaching 1 o'clock. Sorry, it's 12, almost 12:40. Okay, uh, if we have time, we will come back to discuss these examples again. So this is about the graphical methods, which is the same as the files that I left it in the uh, 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 room, classroom. So you can also find out. Uh, okay, next week, we will continue in this chapter. We are about to finish the storage capacities determinations, and next week we will talk about the pumping system, which is also quite a big subject. Please be prepared for the 3 hours. And anyway, for today afternoon, we'll meet again in the lab.